Surface area of revolution. Let's start by trying to understand and visualize a surface area of revolution. If a curve is rotated about a line, a three-dimensional surface is formed called a surface of revolution. So here we have this function y equals f of x, and it looks like it's defined from 0 to 2. And what we're interested in is rotating this curve about the x-axis. So we're thinking about taking these individual points and revolving them around the x-axis. Well, it's going to create this surface of revolution. It's hollowed out. So we're not talking about taking the area under the curve and rotating it to create a solid. We're now just talking about, again, taking the points on a curve and revolving those, and we're thinking about that surface of revolution, and we want to find the area of that surface. Now let's try to understand the formula for finding the surface area of revolution when we rotate about the x-axis. So we're going to need f of x to be greater than or equal to 0 and have a continuous derivative on the interval from a to b. And this is really just saying the function has to be above or on the x-axis and has to be smooth. A continuous derivative means it's going to be a nice smooth curve. The surface area, S, formed by revolving the graph of y equals f of x about the x-axis is, in terms of x, so first we're going to do this in terms of the x variable. So it's going to be, obviously, an integral. The integral from a to b of 2 pi f of x times the square root of 1 plus the quantity f prime of x squared dx. So what's going on here? Where is this coming from? Well, part of this formula should look familiar. If I go ahead and cross out the 2 pi f of x, the integral from a to b of the square root of 1 plus the quantity f prime of x squared dx, that is just arc length. So over here on this graph, this is the curve, let's say y equals f of x, and we're looking at it from some x equals a to x equals b. So this formula here would tell us the length of the arc. And so remember, we took a closer look at that formula and we took those tiny little pieces and we made them infinitely small and we found the length of this arc. But now we're taking this arc and we're rotating it around the x-axis to form this surface area of revolution. And so that rotation is where we're getting that first part of the formula here. So let's try to take a look at where this 2 pi f of x is coming from. And we'll take a look at an individual x value here. So some random x between a and b, and focusing closely on that. Well, if I think about taking a cross section of that surface area of revolution at this x value, the cross section is going to be the perimeter of a circle, otherwise known as the circumference of a circle. So this slice, we're not taking the full circle and thinking about area, we're just thinking about that border of it. And so the formula for circumference of a circle is 2 pi r, 2 pi times the radius. Well, at this one x value, what is the radius of the circle? Well, at this x value, the output is the y value. The output is y, or y equals f of x. So the circumference is 2 pi y, or 2 pi f of x. So if we're trying to find the surface area of revolution when rotated about the x-axis in terms of the variable x, then we're going to have the 2 pi f of x and then times what basically looks like the arc length formula. All right, so this is in terms of x. Now, just depending on what we're given, it may be better to do this in terms of the variable y. So if our function is given as a function of y with, again, a continuous derivative, and it's defined on some set of y values from c to d, with this time y being greater than or equal to 0, then our formula is going to be the integral from c to d of 2 pi y, so now it's just that individual variable y, everything's in terms of y, the square root of 1 plus the quantity g prime of y squared dy. Let's jump into an example. Here we want to find the area of the surface generated by revolving the curve y equals rad x on the x interval from 3/4 to 15/4 about the x-axis. So here we're rotating about the x-axis. Our limits of integration are x values. Our function is given as a function of x. So we're going to go ahead and set this up in terms of the variable x. So let's go ahead and start by taking the derivative. We know that's going to be part of this formula here. So here y prime, the derivative of rad x is 1 over 2 rad x. So that's one of the derivatives that we should kind of be able to quickly take in its nice simplified form. So here is the derivative, and then let's start to set up our integral. So the surface area is going to be the integral from 3/4 to 15/4 of 2 pi, and then that radius is going to be f of x. So the function radical x. So it's like 2 pi y, but I don't want to put the variable y here because these are x values. So what I want to put here is just radical x and then times the square root of 1 plus the derivative squared. So that's 1 over 2 rad x quantity squared dx. So here we want to be careful. We don't want to put the variable y because everything here is in terms of x. So we put y is equal to f of x. And then let's go ahead and try to simplify this and then see what integrand we're working with here. So I'm going to go ahead and pull the 2 pi out since that's a constant multiple. And then I have the integral from 3/4 to 15/4 of the square root of x, and then times the square root of 1 plus 1 over, so if I take 1 squared, that's 1, and then 2 squared is 4, so I'm going to have 4 on the bottom, and then radical x squared is x, so I'm going to have 4x on the bottom. And so what I can go ahead and do, I have, and then I forgot dx. What I can go ahead and do is use properties of radicals when I multiply here. I get to multiply the parts underneath the radical together. So I can turn this into 1 square root. So 2 pi, the integral from 3/4 to 15/4. And then the square root of x times 1 plus 1 over 4x dx. And I'm kind of showing a lot of work here. I mean, we could have just in our head distributed the x in, but I'm going to go ahead and do that now in my next step. So I'm going to have 2 pi, the integral from 3/4 to 15/4, the square root of x plus 1/4 dx. And this is not too bad at all to evaluate. We're going to go ahead and do this with a u substitution. So I'm going to let u equal x plus 1/4. Then du is just dx. And I'm going to change my limits of integration because these are x values. I'm going to turn them into u values. So even though these were weird fractions, right now this is going to work out quite nicely. So if I substitute in 3/4, u of 3/4, 3/4 plus 1/4 is 4/4 or 1. And then u of 15/4, so 15 over 4 plus 1 over 4 is 16 over 4, which is 4. So my new limits of integration will be nice integer values. And let's go ahead and give ourselves some space. So let's write 2 pi, the integral from 1 to 4. And then we have just the square root of u du, or basically u to the 1/2. So we're looking at 2 pi. And then the antiderivative of u to the 1/2 is u to the 3/2 times the reciprocal 2/3, evaluated from 1 to 4. And so we have, I'm going to put 4 pi over 3, and then I'm going to have 4 to the 3/2 minus 1 to the 3/2. All right, and then 4 to the 3/2, we take the square root of 4, which is 2. 2 cubed is 8. And then this is just minus 1. So in here I have 8 minus 1 times 4 pi over 3. So finally we're going to have 4 pi over 3 times 7 for a final answer of 28 pi over 3. And that's it. So that is going to be my surface area of revolution. Before moving on, I want to take a quick look at the graph. So y equals the square root of x between 3/4 and 15/4 is this curve here, rotated around the x-axis, is going to form this surface area of revolution that forms these circumference cross sections here. And so if we pick just a random x value in the middle, then the radius at that x value is f of x. And so that's what we used for finding that circumference, is that f of x. And so this is kind of just like a rough sketch, a little bit of what that surface area of revolution looks like and why we used f of x, because everything was in terms of x, our limits of integration, our function. And so we need to be consistent and keep that as a function of x. In this example, we want to find the area of the surface generated by revolving the curve x equals 1 plus 2y squared on the y interval from 1 to 2 about the x-axis. So this time we have our function as a function of y and our limits of integration, or our interval, as a set of y values. So we are going to go ahead and set everything up in terms of y here. So we're going to start by taking the derivative. X prime is just 4y. And now the surface area is going to be the integral from y equals 1 to y equals 2 of 2 pi, just the variable y. So remember, these are y values. These are y equals 1 and y equals 2. So we do want to put just the variable y here. And then we're going to have the square root of 1 plus the derivative, which is a function of y, squared. So quantity 4y squared dy. And so we're going to go ahead and I'm going to pull the 2 pi out. It's just a constant multiple. The integral from 1 to 2, y, and then the square root of 1 plus 16y squared dy. And this is going to be a nice u substitution. So if I let u be 1 plus 16y squared, then du is 32y dy. If I just have y dy, I'll just go ahead and divide by 32. So 1 over 32 du is y dy. And then I'll change my limits of integration, which are y values, to u values. So u of 1 is 1 plus 16, so that's just 17. And then u of 2, so if I plug in a 2 here, 2 squared is 4, 4 times 16 is 64, plus 1 is 65. So our new integral is going to be 2 pi, and then I'm going to have that 1 over 32, the integral from 17 to 65, and then the square root of u, which is u to the 1/2 du. So in the front here, we'll have pi over 16, and then u to the 1/2 becomes u to the 3/2 times 2/3, evaluated from 17 to 65. So not quite as nice of numbers as the last one here. Let's go ahead and multiply the pi over 16 times 2/3. So 2 goes into 16 8 times. So we're going to have pi over 24 in the front. And then we're going to have 65 to the 3/2 minus 17 to the 3/2. And I can't evaluate either of those without a calculator. So I can't take the square root of 65 or the square root of 17. So this is my exact answer. If we wanted an approximate answer, the approximate answer is about 59.43. It's about 59.43. And so just to also show a little bit of the graphical interpretation of what's happening here. So x equals 1 plus 2y squared would be a full like sideways parabola. So it's going to look something like this, but I'm only interested in it from y equals 1 to y equals 2. So basically it's just going to be a little portion of a parabola, so something like this. So very similar. look to the square root of x from the previous example. And again, we are still rotating this around the x-axis. And so our little cross sections, right, are still basically going to need to look like these circles, the circumference of a circle that's perpendicular to the x-axis. So it's going to have a very similar shape. But what's happening is we're picking a y value in here. So I'm going to go ahead and sort of pick a random y value between 1 and 2. And we're saying at that y value, I'm going to go ahead and create my circle to look at the circumference at that y value. And so we're looking at now this y as the radius of that circle. So the formula 2 pi y, so it's this y right here, and then this is the equivalent arc length formula, but just as a function of y. Now we can take a curve and rotate it around the y-axis and also get a surface area of revolution, and we get analogous formulas. So let f of y be greater than or equal to 0 and have a continuous derivative, this time on c to d. So in our image right here, we're saying that we have this x equals f of y curve, and whoops, we're looking at that from c to d. And we're rotating around the y-axis this time. And so the surface area formed by revolving that around the y-axis in terms of y is the integral from c to d, and then 2 pi, and then f of y, because that radius x is f of y, and then the square root of 1 plus f prime of y, quantity squared, dy. So similar concept, again, this time we're just rotating around the y-axis. And if we needed to do this in terms of x, so we're still rotating around the y-axis, but if we want to do this in terms of x, and we have a function of x given and our limits of integration, or our interval is in terms of x, then we need to make sure and use the x variable here. And again, x limits of integration and our derivative as a function of x. In this example, I want to find the area of the surface generated by revolving the curve y equals 1 minus 2x, where y values are given as the interval from 0 to 1 about the y-axis. So here's where things start to get tricky. So now we're not only possibly rotating around the x-axis, but we could be rotating around the y-axis. And then here, y is given as a function of x, but my interval is given as a set of y values. So it's pretty easy to get mixed up. So what I would recommend is drawing a graph. So here I have y equals 1 minus 2x. So this line has a y-intercept of 1 and then a slope of -2. So we're going to go, down 2 over 1. So here what I'm going to do is I'm going to put 1 right here. I'm only interested in this from y values from 0 to 1. So I'm only going to draw this little portion right here. So the x-intercept would be 1/2. So this is the arc that I'm rotating, right? Or the piece of the curve that I'm rotating. So from y values from 0 to 1. And I'm rotating around the y-axis. So what's helpful is basically to draw a cross section, which is, that circle, because we're interested in the circumference of that circle. So if I just pick some random y value there, and I think about that circle, then what I really need is the radius of that circle. I need to think about that radius right there. So that radius, right, is an x value. So this is a little horizontal line because I'm rotating around the y-axis. So this is some x equals f of y. Now, let's go ahead and think about the limits of integration. So the ones that were provided to me were y values from 0 to 1. Because I drew the sketch, I could also do this in terms of the x variable. So here, if I did this in terms of the x variable, then my limits of integration would be 0 to 1/2. If I do them in terms of the y variable, it's 0 to 1. So let's go ahead and set up both. So here, if I set this up in terms of the y variable, then we're going to have s is equal to the integral from y equals 0 to y equals 1. And then we're going to have 2 pi. And here's where we want to be careful. It might be tempting to put a y right here because you might be thinking, okay, but I need it to all be y variables, right? But what I really want is a representation of this radius right here. So I have to actually put f of y. But again, what was I given? I was given a function of x. So what I would need to do is solve this to be a function of y. So what I would have to do is, let's say, add 2x to the left and subtract y to the right, then divide by 2. So x is equal to 1 minus y all over 2. So x is now a function of y. I need to put f of y right here. So I'm going to have 2 pi and then f of y, which is 1 minus y all over 2. And then the square root of 1 plus the derivative of this, x prime. So I'm going to have to find x prime. And remember that this is just 1/2 minus 1/2 y. So the derivative is just negative 1/2. It's just a constant. So I'm going to have 1 plus the derivative squared, negative 1/2 quantity squared, and then dy. So here, some nice things happen. So the 2 over 2 cancels. Let's go ahead and pull a pi out to the front. So I have pi, the integral from 0 to 1 of 1 minus y. And then inside here, this is just a number. So this is 1/4 plus 1, so 5/4. So this is the square root of 5/4 dy. The square root of 5 over 4 is the square root of 5 over just 2. So let's pull that to the front. So I have the square root of 5 over 2 pi. And then I'm just integrating 1 minus y dy. And so if we do that, we'll leave rad 5 over 2 pi, and then we have y minus y squared over 2, evaluated from 0 to 1. If I plug in 1, I'm going to get rad 5 over 2 pi, and I'll get 1 minus 1/2. If I plug in 1 into both y's, and then minus just 0. And so 1 minus 1/2 is 1/2. If I multiply that by this radical 5 over 2 pi, I end up with radical 5 over 4 pi as my answer. Again, setting this up in terms of the variable y because those were the limits of integration provided. But I could have set this up in the variable x. So an alternative would be the integral from x equals 0 to x equals 1/2. And then we're going to have 2 pi. And again, the key is understanding that I want this distance here, that's x. That's going to be the radius. So it's going to be 2 pi x, and then the square root of 1 plus, and then I need the derivative of this original function. So I need y prime of x to go right here. So let's go ahead and kind of bring that down. So y prime is just negative 2. So we're going to have negative 2 squared and then dx. Okay, so here, this underneath the radical is just 5. And then there's this 2 in the front right here. So I'm going to go ahead and bring out I'll put the 2 first. 2 rad 5 pi, and we're integrating from 0 to 1/2 of just x, right? So here, the antiderivative of x is x squared over 2 from 0 to 1/2, and then I have this 2 rad 5 pi. And so what we're going to have, 2 rad 5 pi, and then if I plug in 1/2 and square it, so I have like 1/2 and then 1/2 squared, that's going to work out to give me the same answer, right? Because this and this are going to cancel. And so I end up with radical 5 over 4 and then times pi. So there's those two different setups. I had to work for the limits of integration if I was going to do things in terms of x. But then if I did this version in terms of y, I had the limits of integration, but I had to solve my equation to be a function of y. So there's a little bit of work either way, but it's just really important to understand the idea of the radius that we're talking about. So it matters if we're rotating around the y-axis versus if we're rotating around the x-axis, right? Then our radius is going to be perpendicular to the axis of rotation. So if we're rotating around x, it would be perpendicular to the x-axis. We're rotating around y, so the radius is perpendicular to the y-axis. Before our last example, here's sort of a general summary. So if a curve is smooth, meaning its derivative is continuous on an interval, and it's revolved about an axis, then the surface area can be generalized by saying it's the integral of the circumference times that arc length element, right? And the circumference can be generalized to say that it's 2 pi times the distance to the axis, right? Whichever axis we're rotating around. And then of course that arc length element is the square root of 1 plus f prime of x quantity squared dx, or the same thing with functions of y, dy. We use x's if we're integrating in the variable x and y's if we're integrating in the variable y. So this is sort of just a really general type of summary. The main piece here is that the circumference is that distance to the axis that we're rotating around. Here, let's find the area of the surface generated by revolving the curve y equals 1/4 x squared minus 1/2 natural log x. The x interval is from 1 to 2, and we're rotating about the y-axis. So let's go ahead and set up our integral. We'll have s is the integral from x equals 1 to x equals 2. So we have the interval is in x and the function is a function of x. So we'll say the integral from 1 to 2 of 2 pi. And then again, everything here is going to be in x, and we're rotating around the y-axis. So we're going to go ahead and have x, so that distance from the y-axis is a horizontal line x. So we're going to have x, and then the square root of 1 plus the derivative as a function of x. So let's go ahead and find the derivative over here, y prime. Here with the power rule, we'll have 2/4, which is 1/2. So we'll have 1/2 x minus 1 over 2 times the derivative of ln x is 1 over x. So what I have here is x over 2 minus 1 over 2x. That's my derivative as a function of x, and then we have to square that. So this is going to be heavier on the algebra. So I have x over 2 minus 1 over 2x squared dx. So the algebra here is going to be similar to those arc length problems we've done in the past. I'm going to go ahead and take out the 2 pi. So we'll have 2 pi, the integral from 1 to 2. I have an x on the outside, and then I have this square root of 1 plus. Now here, remember that I do have to distribute all this out, so I cannot distribute the exponent, right? I technically have to like FOIL all of this out. And so if we go ahead and think about maybe doing that off to the side, if we can do it in our head, that would be wonderful. So x over 2 and then minus 1 over 2x times itself. So if I do that, I'm going to get x squared over 4. And then outer here, the x's are going to cancel. So I'm going to have a minus 1/4. And then same thing with inner, the x's are going to cancel. I'm going to have another minus 1/4. And then finally plus 1 over 4x squared. And then these middle terms combine, minus 1/4 and minus 1/4 is minus 2/4, or minus 1/2. So I'm going to have x squared over 4 minus 1/2 plus 1 over 4x squared. So we'll go ahead and substitute that in here. And again, ideally, if we can just jump straight to that in our head, that would be great. So this is substituted in now. And then 1 and negative 1/2 are like terms. So in this next step, we'll have 2 pi, the integral from 1 to 2, x, and then the square root of x squared over 4 plus 1/2 plus 1 over 4x squared dx. So I am keeping that constant in the middle, and that's because of that algebraic component that we're about to use, is that this is a perfect square trinomial under here. So we're going to have 2 pi, the integral from 1 to 2x, and then underneath this square root here, this is something squared. It's x over 2 squared. This middle part here is going to end up being double these two outer pieces squared. So the outer piece 1 over 2x quantity squared. Turns out 1/2, right, is 2 times the a and the b. So this 1/2, I'm just going to leave it as 1/2, but it really is like 2 times x over 2 times 1 over 2x. So we can see the 2's cancel and the x's cancel. We've convinced ourselves of that, and that's a nice feature, because then the part underneath the radical becomes just quantity x over 2 plus 1 over 2x squared, so that the square root and the square cancel. I still, of course, have the x in front. But now I have a much nicer thing to work with. So I still have this x in front, but the square and the square root cancel. So I'm just going to multiply this x to the pieces underneath. So we're going to have 2 pi, the integral from 1 to 2x multiplied by x over 2 plus 1 over 2x dx. Now we have 2 pi, the integral from 1 to 2 of 1/2 x squared plus just 1/2 dx. And so the antiderivative here is going to be x cubed over 3, so 1 over 6 x cubed, multiplying that 1/2 and 1/3, and then plus 1/2 x evaluated from 1 to 2, so that 2 pi in the front. So here is just some arithmetic, right? So we're going to plug in that 2 into both x's. 2 cubed is 8. 8 over 6 is 4/3. So we're going to have 4/3 plus, if I plug in 2 times 1/2, that's 1, minus, if I plug in 1, I'm going to get 1/6 plus 1/2. And skipping some of the arithmetic that's in there, I am going to end up with a final answer of 8 pi over 3. And that's it.